All right, can I get everybody's attention? I'd like to get started tonight. Today we're kicking off our spring 2008 lecture series for physics and space science. And we're lucky enough here to have our first Harold Shapley lecturer, and that is Professor Wendy Bauer from Wellesley College. Wendy Bauer is a professor at Wellesley College. She joined the faculty there in 1979, having spent 2 years as a postdoctoral fellow at the Harvard-Smithsonian Center for Astrophysics. She graduated from Mount Holyoke College in 1971 with a BA degree in astronomy and physics, and received her MS and PhD degrees in astronomy from the University of Hawaii in 1974 and 1977, respectively. And today she's here to talk about searching for life, extraterrestrial life. And with that, I'll turn it over to Bauer.
And can people hear me in the back row when I talk in a normal voice? Okay, good. Harlow Shapley, by the way, is the man who did for our galaxy what Copernicus did for our solar system. He's the one who figured out that we were not at the center of our galaxy, and he did that by observing a number of globular clusters. A globular cluster is a conglomeration of hundreds of thousands to a million stars that are all together in a big spherical shape, and there are certain variable stars within those clusters that when we measure their brightness, we can figure out their distance. And he figured out that this distribution of globular clusters was not centered on the sun and the solar system, and that it made a lot more sense for the galaxy to be centered on them than on us. And so that's where he has his claim to fame. So what I'm going to talk about today, the search for extraterrestrial life, I really am going to present sort of the majority opinion or thoughts among astronomers, sort of the conventional wisdom or best guess at this point. And there are plenty of astrobiologists who are working on other alternatives other than the carbon-based, water-based life I'm mainly going to be talking about. So it may seem that I'm really being sort of Earth-centered in this talk, but we got to start somewhere. Why carbon-based? Why do we, all Earth life is carbon-based. It's all based on DNA. And the reason that we understand that chemically is that the carbon atom has 4 electrons in its outer valence ring, and so it has room for 4 electrons to make chemical bonds with it. And the particular chemistry that it has allows it to make the very complicated molecules like DNA that can reproduce and have the very complicated chemical reactions to build up the big proteins. Now the next element beneath it in the periodic table is silicon, and it has those same electron configuration, but when you put silicon together with oxygen, it just loves to make rock instead of carbon dioxide or carbon monoxide that's a gas. And carbon is very, very abundant in the universe. It's made in a lot of stars, and therefore we think that that's the best bet, but not the only bet, would be that other life is based on carbon. And all Earth life is based on and requires liquid water for at least a large period of the organism's life cycle, and we believe that there are reasons for that. The water molecule is polar, the charge isn't distributed evenly, and that makes it easy for it to pick up other molecules and get them into solution and travel around within the cell and bring the nutrients wherever they need to go. And water is liquid over a lot larger range in temperature than many other molecules are. And it's the right range and temperature for the carbon chemistry to be going. And water is also not necessarily liquid water, but the elements from which water is made, the hydrogen and oxygen, are also very, very abundant in the universe. Hydrogen and helium having been here since the Big Bang in great amounts, and oxygen being another element that is often made in stars. So I am going to restrict this talk to thinking about, for the most part in the talk, thinking about carbon-based liquid water requiring life. But again, realize that there are astrobiologists who are working on other options. Now, the search for extraterrestrial life was not a really popular subject for astronomers for a lot of years. And the reason for this was had to do with our understanding of the formation of the sun and stars and planets. And there were, when I was a little kid in the 50s reading astronomy books, there were two competing theories for how the planets came to be formed. And one of which, and that's the one we understand to be the case today, a cloud of gas and dust will contract down and the star will form and the planets will form and the debris left over from that. The other theory was that two stars would pass fairly nearby each other and the gravity of each of the stars would pull material off the other star, and that material that was pulled off would then condense to make the planets. Now, if that were the leading theory for the formation of solar systems, it turns out that there would be only a very, very few solar systems with planets in our whole entire galaxy. One of the homework problems I will give in my introductory astronomy classes is to say if the Earth were the size of a grain of salt, say 0.5 millimeter across, how big would the sun be? And it turns out that the sun would be the size of a light bulb, and they'd be about 20 feet apart. And then the next question is, how far away is the next other star on a scale like that? And it people will guess, oh, over in the next room or across the street or something. It turns out to be about 1,000 miles away. That if our sun were the size of a light bulb, the nearest other light bulb would be 1,000 miles away from here. And a sophomore level astrophysics question we ask the students is, if you know how large the stars are relative to their separations and how fast they're moving, how often would they collide? And it turns out there would only be a half a dozen or a dozen close enough collisions between these stars to make solar systems. So all of a sudden you go down from having several hundred billion possible solar systems to a dozen, and there's not going to be nearly so many civilizations if you only have a half a dozen solar systems in the whole galaxy. So in the early 50s, the theoreticians were having trouble figuring out how a single cloud of gas and dust could make planets. But then by the late 50s, they'd worked past their difficulties with that model for solar system formation, and all of a sudden they were suddenly given the thought of hundreds of billions of stars within our galaxy, each of which could have potentially formed planets. And then it became popular to think about looking for extraterrestrial life. And the first people who really did much about it were radio astronomers, because they thought it might be possible that a civilization could beam a radio message at us that we could detect to be different from just normal radio astronomical source. And toward the end of the talk, I'll get into how we might and are still looking for and how we would separate an artificial signal like that. But the first fellow to do much about it was named Frank Drake, and he organized a conference of radio astronomers, late 50s, early 1960s, somewhere 1959 or something like that, where, okay, now this thing's completely, okay, there we go. They, in their conference, they tried to work through the guesstimates of how many civilizations there might be. And they came up with this equation. I'm not going to test you on this at the end of the talk, but it provides a really good way, I think, for somebody to organize a lecture about the search for extraterrestrial life, to run through these various letters in this equation, talk about what they mean and how we restrict our thoughts. N here stands for, well, I'm going to do it one at a time here. N stands for the number of intelligent civilizations in our galaxy. And we're going to restrict this to our own galaxy. We've got several hundred billion stars here to choose from. The next large galaxy beyond ours is 2 million light years away. That means if they sent us a message and we received it, we say, okay, this is cool, we'll answer back. 2 more million years of light travel time, which is how long the radio message would take. Radio is just another form of light. They send us a message back, another 2 million years elapses. We're not going to have a meaningful dialogue with these folks. So, even the far side of our galaxy is 100,000 light years away. So, the next one here, R sub star, is the rate of formation of sun-like stars. And why sun-like? I'm going to spend a good chunk of the talk talking about why our sun and stars similar to it are the best bets, and how we throw out other stars. because their properties aren't quite as good for the support of intelligent civilizations as a star like our sun is. The rate per year instead of the total number is in there just because of other factors in the equation, but and then for the purposes of this talk, if R sub star is big, then there's going to be more stars to pick from. What fraction of those sun-like stars actually form planets? And at this point, a good guess on that one is probably, unless it's a binary star system, which encompasses about half the stars in the sky, we think now the odds are really good that a single star will form along with its planets. And I'll show you a little bit of some of the evidence we have that that's probably true. Once you have planets in a solar system, how many planets on average per solar system are Earth-like enough, and by this I mean liquid water available per solar system. And so I'm going to go through the second big part of the talk will be to go through a tour of our solar system to show places that do have liquid water at the surface, us, other places that have liquid water maybe below the surface, and what can go wrong for a planet so that it doesn't have liquid water. So there'll be that solar system tour to pin down this number of Earth-like planets. And one thing I'm going to jump ahead here and bring this in now. We have now begun to find planets around other stars. And we don't do it yet by seeing a little faint dot next to the bright star. But we do it by, for the most of the extrasolar planets have been found by looking at the planet moving around the sun. The star also tugs the star around a little bit. You know, I said Shapley did for the galaxy what Copernicus did for the solar system. Copernicus says, the planets are going around the sun and the sun is still, but the sun isn't still. The sun's being pulled around a little bit by these planets that are going around a lot. And if you think of a seesaw or a teeter-totter, if you get on a teeter-totter with somebody that's the same mass or weight that you are, you sit equal distances from the center and you move up and down about the same amount. Well, the sun and the Earth and the sun and any other planet are orbiting around their common balance point. So if I were to go to the... Now my kid has almost the same weight I do, still a little bit smaller, but now that she's grown all up. But when she was little, if I were to take her to the play park and get on the teeter-totter, I had to sit really close to the balance point. She sat way out here, and I'd go up and down a little bit. But this is the sun, and that's the Earth. But we're able now to have, through the Doppler shift, which you've all heard, the siren comes at you, as the siren's coming toward you, the sound waves that it emits are kind of crunched up. Each wave is emitted from a little closer to you and takes a little less time to get to you. And that compression in the sound waves we hear as a higher pitch. As the siren goes away, then each wave is emitted from a little farther away, and it's like the waves get stretched out and we hear a lower pitch. And the same effect happens for light. Although since the speed of light is so much faster than the speed of sound, you have to have a lot faster speed before you can detect it. One of my favorite physics problems to assign has a guy runs a red light, and the cop stops him and said, "You ran the red light," and he challenges it and goes to court and said, "I did not run the red light. I was approaching the light and the Doppler shift shifted the red light to green. So I went through." So the judge says, okay, he knew physics, and he says, "I'm going to fine you $1 for every mile per hour you were going over the speed limit," and it's like a $150 million fine. So to get that huge of a shift, you have to be going really fast. But the instrumentation that has been developed will let us take a star that is tens to hundreds of light years away and measure it moving toward or away from us at the speed of a fast bicyclist. And that's how fast Jupiter is pulling our sun around. And so what we do now is we monitor the light coming from these stars, and we can, if the star is moving back and forth in a very steady pattern because it's being pulled around in the orbit by its planet, that's how we find the planets. Now we had it all worked out why in our own solar system you've got the sun and you got 4 rocky, small planets close by, and you got 4 big gas liquid giants out beyond that, and then the little icy things out beyond that. We figured that all out. We can understand why that happened. So that's what we expected to find, that any sun-like star would make little planets close by. What have we found? Big ones close in. Now, this is in about 10 to 20% of the sun-like stars we have observed. We've found those things. We're caught totally by surprise. The theoreticians say, oh, but if they can't form in close, but they might form way out there and then migrate in, but they'd boot all the little ones in when they did it. So I went to an American Astronomical Society meeting maybe 10 years ago, right after these hot, close-in Jupiters had been found, and the theoreticians told us about how these things can move inward. So up goes my hand at the end of the talk. Well, then how come Jupiter stayed out in our solar system? I said, well, we can tweak the theory to... But now I'm kind of like throwing that out aside as we can tweak the theory, but they really are working out the dynamics of the planet-forming process. And if there were lots of heavy elements in one of these disks, bigger planets would form, and there'd be more interactions, and it would be more likely that the planets would come inward. And they are finding more planets close in around the more metal-rich stars. So it's not just a kind of a side throw-off comment, but what it does do is bring down that number of Earth-like planets. If 10 to 20% of the sun-like stars that we've observed now have in close to the right distance from the star, the giant planets with no solid surfaces. So that brings down the likelihood. But it is a selection effect. Those big ones in close are the easy ones to find. We can't find Earth-sized planets by that method yet, and we may not be able to for a long time. So to find Earth-sized planets, we have to use other techniques, which I'll talk about a little bit at the end of the presentation. Once you get an Earth-like planet, how likely is it that life will evolve on that Earth-like planet in the liquid water? And most biologists and astrobiologists will call that one probability of 1. It's once you get the right conditions, life is very likely to form. They have in the lab reproduced the basic amino acids and even come so far as making simple RNA-like structures. And another reason why we believe, and there's a lot of belief in here, although there's scientific background to the belief, that life formed early on our planet. For the first 500 million years of our 4.5 billion year history, we were being really badly pummeled by the leftover debris from the formation of the planets. And it would have been really difficult for life to get a foothold while all its huge impacts were probably boiled the oceans away a few times in our history occurred. And we can see the record of that pummeling on our moon. But 3.85 billion years ago is the first probable indication of life from different chemical abundances within rocks. That's somewhat controversial, but there's some stromatolite fossils that are 3.5 billion years old that look very much like current-day microbial mats. So it looked like once the conditions settled down on the early life, on the early Earth, primitive life formed quickly, which means it's got to be pretty easy to do. But then it took a lot longer before intelligent life evolved. That depends on what you count as intelligent. The radio astronomers, for their definition, used capable of building a radio telescope that could produce a signal strong enough to transmit our entire galaxy and be picked up by a similar telescope on the other side. And we've had something like that for... I forget exactly when Arecibo was first built, but it was refurbished in 1974. And at the end of the talk, you'll see a picture of our telescope that qualifies us to be considered intelligent. Now, whales and dolphins clearly have a large amount of intelligence based on the complicated communications that they do between themselves. But it's a whole nother level to try to imagine coming out from a completely water-based environment and getting on and building a radio telescope from beneath the ocean. So we're not counting them yet. Now, F sub C is one more. If you do have the intelligence, do you actually build the telescope and make the communication across the galaxy? We've built the telescope, but Our own deliberate communication efforts are very minimal, and I'll save that part for the end of the talk. The final letter here is, how long does that civilization last? Our sun is 4.5 billion years old. There are plenty of stars that are 5 billion years old and plenty of them that are 3 billion years old. What if our other civilizations took as long as we did to evolve to the point to be able to build these telescopes? And what if we then blew ourselves up 50 years later because we also built the bomb? And we only lasted 50 years, and we just missed this other civilization that formed 100,000 years or 1,000,000 years from now, or 1 billion years from now. Then we wouldn't be very likely to have any two of those civilizations be around at the same time. However, we have a total of about 1 billion years left to us before our sun becomes bright enough. It is steadily, gradually increasing in brightness, not getting hotter so much, it's getting a little bit bigger with time, and it is therefore getting a little bit brighter. And after about 1 billion years, the sun will be bright enough to basically boil off our oceans and kind of put paid to us unless we can do something about it. And there are people talking about how do we get an asteroid into an orbit such that it gravitationally interacts with Earth just enough to gradually push our orbit out a little bit as the sun expands in time. But so, the computer maxim, or the maxim of the computer age, garbage in, garbage out. This is an equation, but the number, I should have learned this afternoon where I have to press the pointer, but the number on the left-hand side of this equation is only as good as all the numbers on the right-hand side, and the worst number on the right-hand side its error is going to go in here. All I can say is n is greater than or equal to 1. But there are optimistic people who say if L is a billion years and all these other numbers are high, then there are probably tens of thousands of civilizations out there, and the nearest ones to us are within a few tens of light years. If you put in pessimistic numbers, we're it. But this does allow me to say, okay, first I'll talk about what stars are good, and then what planets are good, and then what we're actually doing to try to communicate and or determine, well, two different parts. The search is look for Earth-like planets around other stars, and then listen for radio signals. So the last part of the talk will be those. So as far as which stars are capable of having life around them, got to give you one more equation. This is the equation that always shows up in the cartoon with the scientist in the little white lab coat that is writing incomprehensible things on the chalkboard. Well, it took Einstein to figure it out in the first place, but it doesn't take an Einstein to understand it now. E is energy, m is mass, c is the speed of light, which is a big number, and when you square it, it's an even bigger number. And m is for mass. If you take a little tiny bit of mass and annihilate it and convert it into energy, you get a lot of energy out. And what our sun is doing, it is taking 4 protons, or 4 hydrogen nuclei, fusing them together into a helium nucleus, and the helium nucleus has 0.7% less mass than the sum of the 4 protons that went into it, and that's where all our energy comes from, whether it's the solar power now or oil that is sold by companies in Houston to burn. It's all came originally from E equals mc squared in the interior of our sun. Our sun has a total of 10 billion years worth of hydrogen. It's used up about half of that. What I'm going to do now is go through a brief history of the life of a star in pictures, starting from the Baby album. Stars form from clouds of gas and dust that are in between the stars, and when an astronomer says dust, they don't mean the stuff that's under the bed at home. They mean little solid particles of generally silicate rock, just like the most common rock type on Earth, or carbon soot, and some of that will have ice mantles around it. This beautiful pink stuff is all hydrogen gas. There'll be other elements mixed in with it, but the pink color is produced by hydrogen. This one's called the North American Nebula. I was up here a couple days ago, and now I'm down here, and I'll go back up there in a couple of days. This is the Rosette Nebula, where for the hydrogen to glow pink like this, you have to have some hot, bright stars nearby causing it to glow. But where the stars form is in dust, dark patches, where the densities are higher and the temperatures are cooler. This is a very famous dust cloud called the Horsehead Nebula, and the amateur astronomy community was allowed to pick some 10 or 20 of their favorite objects, and then the Hubble telescope went out and took images of those for their heritage program, and this is what the Horsehead Nebula looks like as observed by the Hubble. It's dark clouds like this where the stars are forming. And now gravity is always, this is a really, here's another one of these dark patches of dust blocking the light from behind it from reaching us. And this is another very famous Hubble telescope picture of that particular dust cloud. And there's these little round blobby things at the edge of this cloud where new stars are forming and blowing the dust away. Throughout a star's entire life, gravity is trying to crunch it together. It needs some other force to push it apart. Now, it's a good thing that gravity pulls it together to start with. If this E equals mc squared and fusing hydrogen to helium is such a wonderful source of energy, how come we still have to burn oil? It's because it's very difficult to get this fusion process to go. Take two protons. In order to get them to fuse together to start building that helium nucleus, you have to get them right next to each other, which they don't like. Off they go. They repel each other, but if you can get them moving fast enough, they'll collide and they'll fuse. Now, what we call temperature is really just a measure of how fast particles are moving. And the faster they're moving, the higher the temperature. And the faster they're moving, the more likely they are to get close enough before they repel. You need a temperature of 10 million degrees Kelvin, which is about 18 million Fahrenheit, for this fusion to occur. So stars like our Sun, the gravity of the outer layers compresses the core to high enough temperatures for this fusion to happen. And that's what it takes to define a star. Enough mass to crunch the center. So anyway, the Orion Nebula here, if you're familiar with the constellation Orion, there's the 4 corner stars and the 3 stars in the belt, and then there's 3 stars that hang down in the sword. The middle star in the sword is really this big bright gas cloud with a bunch of stars forming in it. And these are actually with more Hubble data where they have observed these small young stars and that they have these dark dust disks around them that are like the size of our solar system. So they are actually seeing disks around stars, and they're starting to see the planet formation process take place. So, as the stars contract down, the centers, when they get hot enough for the fusion to occur, they produce additional pressure which pushes back against the gravity, stops the contraction. They blow off the outer layers of gas and dust, and the star is now able to shine for a very long, steady phase, the longest, steadiest phase of its lifetime. There will be a slow increase in brightness during that, but not much. This is a constellation, small grouping of stars within the constellation Taurus called the Pleiades. And there are a couple faces that were at my afternoon talk. That's the one that's my friend, that my research star has a spectrum a lot like that one. But it's fun to put stellar evolution talks like this, to put the Pleiades in there and say, here is a young cluster still surrounded by a bunch of the gas and dust from which it formed. Well, we now know that the Pleiades cluster just happens to be moving through a completely unrelated dust cloud, but it's still a pretty picture, so there it is. But when they blow off the gas and dust, then you have a star. This is our nearest and dearest. I pulled this image off. I was looking for a good image of the sun to pull off the web. There are sunspots and all the. Oops. I should learn that some of these sunspot patches, like that sunspot there, is probably about the size of the Earth. And then this up here is actually the planet Mercury, which was transiting across the sun, and that's why this image ended up on the web. So now our sun has enough hydrogen to last a total of 10 billion years. It's about halfway there. And then after that, it will expand to become a red giant, and the core will have run out of hydrogen fuel, and it will no longer be supported, and the core will contract down, and eventually it will get hot enough to now take the helium, which now has more protons to fight more protons, and be able to fuse that into carbon and oxygen. Now, it lasts 10 billion years. More massive stars don't last as long. Even though they have bigger gas tanks, so to speak, their mileage is much worse. They shine much more brightly. It's like the difference between a little Honda Civic and a giant Winnebago or something. And the giant Winnebago may have a bigger gas tank, but at miles, at gallons to the mile, it has to refill faster than the small one. And so the very massive stars would not, the most massive ones only last a few tens of millions of years, which might be long enough for the first little single-celled creatures to form, but not long enough for radio telescopes to be built. If the process of the evolution of intelligence is it all the same in other solar systems than ours. And by far the more plentiful stars are the little smaller ones than our sun, but they have other problems. And I know if you've looked at the moon, you see that the same face of the moon is always pointed to the Earth. And that happens because a fairly small thing is orbiting fairly close to a fairly big thing. And for a planet around a smaller, fainter star than our sun to be at the right distance to have liquid water, it would probably get locked into that synchronous rotation so that it always kept the same face to the smaller star. Now the optimists say, oh, but if it had a thick atmosphere, that might not matter. But so that's kind of a sticky point. There are some other disadvantages of those small stars, but if they could, they have a lot bigger flares relative to their size and stuff like that. But if you could have life around them, then there could be way much more life out there than if you have to restrict it to solar type ones. So the size of the star matters, and the other thing is the abundances, the chemical abundances within the stars matter. And I'm going to finish the lifetime thing before I go on to why that matters. Once our sun builds its core up to carbon and oxygen, it's not massive enough to compress it to higher temperatures, and the outer layers of our sun will expand and blow away into what's called a planetary nebula. At the center will be left a white dwarf star, which no more nuclear reactions, it just shines from the heat it already has. It will cool gradually off. I'm going to zip through a few really pretty pictures of these. They're nothing to do with planets. In fact, they're probably not very good at all for planets near them. But in a small telescope, one might look like a planet, so they got that misnomer. But a bunch of pretty pictures taken by the Hubble telescope of planet. That one's called the Eskimo Nebula. In a small telescope, it looks like the face with the fur parka hood around it. And this one's the Helix Nebula. This is actually a ground-based photograph, but there are like little knots in it, and a close-up here of one little part of it shows how this outrushing matter kind of leaves the stuff in the wake of these blobs. Now, more massive stars, even though they aren't good places to look for life as we know it, we needed them badly. The Big Bang only made hydrogen and helium and a trace of lithium. And then everything expanded away and cooled, and you need to have higher temperatures to make heavier elements. So it wasn't until you got the stars where when the core fuses one element and stops, then the core contracts and it gets hotter and it can fuse another element and go on. And these more massive stars are hot enough in their interiors to fuse heavier elements all the way up to iron. And all that time they've been able to release energy which pushes back against gravity. But once you get iron, there's nothing you can do to iron to get more energy out of it. You either have to add energy to break it apart into lower mass nuclei, or you have to add energy to make it fuse to heavier elements. And that leads, which can be a whole other talk in itself, when you get that iron core, the star explodes in a supernova and leaves behind either a pulsar, which is a rapidly rotating neutron star, or it leaves behind a black hole. Now, also in the supernova explosion, I got this gold wedding ring on. That's heavier than iron. How do you get iron? Get the elements heavier than iron. But there is a huge amount of energy released in the supernova explosions, and so they can build up all sorts of heavy elements that way. Those heavy elements go out, get recycled into second-generation stars like our sun. Now, for us to have heavy elements in our bodies and have a solid rock surface of a planet on which to live, or even to have the liquid water, you need to have heavier elements than hydrogen and helium. So the first generations of stars that formed right after the Big Bang are not expected to have solid surfaces or heavy elements for chlorophyll or hemoglobin in the blood. So you got to have the ones with enough heavy elements to make the solid surface planets, and maybe not too many, or the giant Jupiters will move inward. But we still have tens of billions or more suitable stars in our galaxy. And we believe that many of those will have planets around them at Earth-like distances. Now, if it's a hotter star, you got to be a little farther out. If it's a cooler star, you got to be a little farther in. But the real estate agent, he sells you the house, and it's location, location, location. And that really is a number one. I like to phrase it in my class, you got to be the right distance from the campfire to be warm enough. But in our solar system, there are two pretty much planet-sized objects that are the right distance from the campfire. But one of them's too little. And if the house is too little, you don't want it. If your family's too big. You also don't want too big of a house. It's too much of a hassle to clean, maybe. In the case of a planet, if the planet is too big, you don't have a solid surface, like Jupiter and Saturn and our outer giant planets. The moon is too small for its gravity to hold on to an atmosphere, and you need an atmosphere in order to have liquid water at your surface. So there is a size range of a planet that you have to be within. Another problem that our moon has is it has been pulled into this synchronous rotation around the Earth. Each part of the moon gets 14 days of sunlight and maybe it's 14 and a half, but 2 weeks of daylight and 2 weeks of darkness. And so the temperature at the noon time, or maybe it's a little past noon, high temperature time on the moon is 250 degrees Fahrenheit above zero. And the temperature at midnight, or closer till dawn, is 250 below. There's this huge range in temperature because the sun is up for a long time and down for a long time. So the planet's day length also has to be reasonable. And if we were rotating a lot faster than we are and had a shorter day, that might stir up winds more on our surface. So there's a restriction on how long the day is as well. Well, location. Now here's our little thin band of atmosphere in the moon, and there's a Gemini spacecraft from which it was taken. No atmosphere on the moon, the standard picture from lunar orbit. This is actually Apollo 11 lander coming back up to reconnect with the command module. And the standard picture of the astronaut on the surface, no atmosphere, so you've got the black, dark sky with no blue sky and no flag. The flag would, if they didn't have the bar across the top, it would just be hanging down like a flag and no breeze. This is Mercury. This is the planet closest to the sun. It's even worse off than the moon because it has, the sun is up for 88 days and down for 88 days, plus it's way closer to the sun. It heats up to 850 above and 250 below at night because there's no atmosphere to hang on to the heat. Then there's the problem with too much atmosphere. When I was a little girl reading astronomy books, Venus is our twin. It's covered with all these clouds. It's the same mass and diameter as Earth within 10%. And these white clouds reflect the sunlight back. And it turns out that the amount of sunlight that reaches the surface of Venus is about the same as reaches the surface of Earth. And clouds, okay, they're reflecting. Our clouds are water vapor. This has got to be oceans and elephant ear jungles and stuff. That was the picture of Venus when I was a kid. Well, the clouds are sulfuric acid. The atmosphere is like almost all carbon dioxide. It's 90 Earth atmospheres worth of pressure. And it's just greenhouse to the max. Venus it lost any liquid water it had too early on. It's the right size house, but it's in the wrong location. 900 degrees Fahrenheit day and night because of the thick greenhouse gas, CO2 atmosphere on that planet. So it's not no good. So now we think about Mars out beyond us. Mars has two problems. Its size, it's about 1/10 the Earth mass, and it has just not managed to hang on to enough atmosphere over time. There are times on Mars where its temperature is warm enough to support liquid water, but its atmosphere is too thin. Water either boils right away and becomes vapor in the atmosphere, or it can be frozen on the surface. But any liquid water that appears on the surface today, and there is some evidence that some does occur in these little gullies and craters, but it doesn't last long. Mars appears to go through very similar seasons to Earth. The seasons are caused not by our distance from the Earth, but from the Sun, but by the tilt of our axis. And we're actually closest to the Sun in January. But the northern hemisphere is tilted away from the Sun in January, and we have longer days, longer nights, shorter days, less direct sunlight than when we're tilted toward the Sun in the summertime, and we have the flipped hemispheres in the seasons. Mars also has a much more elliptical orbit. When we're closest to the Sun, our average sun over the whole planet is only 3% more than when we're far away. Mars, it's 40%. When Mars gets closest to the Sun, the polar cap, which is bright, reflects the sunlight back. The darker rock heat up, and it stirs up these big planet-wide dust storms. So I'm running a little longer than I probably should, so I'm going to have to skip through some of these Mars pictures. But big volcanoes as big as the whole eastern seaboard, a big canyon on Mars that is not water-carved, but that's that canyon compared to the US of A. We've got orbiters that can take incredibly cool, detailed pictures. Taken from orbit, that's like the view. You could see that as well as you were just looking across the Grand Canyon, and we can see that from orbit. And we can do better now than these older pictures. There are dried riverbeds on Mars. Mars had water in its past, but when it lost its atmosphere, it lost the liquid water. More evidence from liquid water in the splatting of craters that formed in mud. So they sent the rovers to look for evidence that there was liquid water in Mars's past, and they built the cameras up on the stalks here to equal about the eye level of an average height woman, so that the pictures were taken, it would look like you were there. Lots of brown, lots of red rocks. And they kept looking for places where the rocks were exposed in outcrops. And the Spirit rover was sent to climb the Columbia Hills, hoping to find some outcrops. And it found some neat ones. But the opportunity, this came from the website. I wish I could have claimed the title for my own. But it landed right in a crater with an outcrop, which is just what they wanted to see. So it went over and investigated the outcrop, and this is a 3 centimeter or 1 1/4 inch square part of that rock, and they found these little round concretions that the chemical. They went to this location because the chemistry that they could tell from the surface had minerals that were usually only made in water on Earth. And they had several different, there's a bunch of those little, they call blueberries, and that's an area where the brush on the rover scraped off the dust off the rock. There's one instance where these blueberries kind of grew together, so they couldn't have been just little droplets that were blasted out in a volcano. There are little slits that are left behind when crystals dissolve out of a water lake. There is evidence for flow in the bedding of these rocks. And so the rovers really did find evidence that Mars had water in its past. And that's a cool picture of a meteorite that one of the rovers found on Mars. And this is a cool picture of when one of Mars's moons does an eclipse across the sun. And then that was Earth as seen from Mars. So Mars is too little, and it has these. Its orbit is not circular enough. And another thing that could go wrong for a planet is if the tilt of its axis was more severe than ours, and the seasons were more severe. So anyway, out to the outer solar system. Jupiter and all these different colors are just different cloud tops. And that's Io, this orange moon that's just completely covered with volcanoes, because it's in so close to Jupiter in an elliptical orbit. It gets in close, gets farther out, and it just gets tugged by the tides of Jupiter, and it causes these volcanoes to erupt all over the surface. The interesting moon is the next one out, called Europa. And, well, this just compares the size of the Jupiter's giant red spot to the Earth, just to show how big Jupiter is. And there's, again, the red spot, so you can just see how big Jupiter is compared to Earth. These guys are the same size as our own moon. And Europa, the interesting one here for us, has these streaky features on it that look like lines and cracks. And the surface, from what we can tell from remote sensing, is like almost all ice. And this is a false color to just enhance differences in the surface properties. But there are these, whoops, that's not the one. I wanted to leave it on this one. These various cracks, these lines, look in places like they have disconnected and then floated around and refrozen. And so one of the theories is that these things are floating around on a liquid water ocean beneath the surface. Another theory was that there was just slushy ice, and like a glacier, it could move like a glacier creeps. But they have other evidence from the magnetic field on Europa that there really is a liquid water ocean underneath there, not the ice. Well, meanwhile, remember that Io is being pulled around Jupiter, and all this stretching and pulling is causing heat to come up through these volcanoes. Europa is being tugged and stretched, but not quite so much. But there is every evidence that we would believe that there might be heat released at the bottom of this probably 100-kilometer deep water ocean. And since the late 70s on Earth, we have found these very interesting communities around hydrothermal vents at the bottom of our oceans. The bottom of the food chain comes from there are minerals that are being spewed up in this really hot water, several hundred degrees Fahrenheit right when it emerges from these things, but it's not boiling because of the high pressure. It's the opposite of Mars water boiling away at low temperatures. And so the bottom of the food chain are single-celled creatures that get their living from chemical reactions on the minerals that are coming out of these hydrothermal vents. And there's just all sorts of really interesting creatures. There are these 4-foot-long tube worms that are they're sort of symbiotic with the bacteria inside the tubes, and then these red things just kind of scoop the water with the bacteria in. And they have bunches of crabs and fish and stuff that have come. Now, again, the bottom of the food chain does not depend on sunlight in these hydrothermal vents. The top of the food chain are creatures that have evolved in higher parts of the ocean and have kind of moved down. But so we would not necessarily expect that this complex of life might have formed around these hydrothermal vents, if such, and we believe they probably do exist beneath the surface of Europa. But as one of my friends who wrote a book about this search for extraterrestrial life says, it's time to go there and go ice fishing. It would be very difficult, though. They have to work really hard at figuring out how not to contaminate. I mean, we've already contaminated Mars a whole bunch of times with probes that have landed, and Mars has contaminated us with meteorites that have landed, and it's possible that meteorites that have been blown up from Earth from impacts have landed on Mars, although that is less likely because they'd have to fight more gravity to get away from us than from Mars. But you'd have to be really, really careful not to pollute with our Earth-like life forms so that you could really tell if there was a separate origin of life. If we find Earth-like life on Mars, we won't know whether it was a completely separate origin or not, or whether it traveled from one of the planets to the other. Another place that liquid water has been found in the solar system is on one of the moons of Saturn. I shouldn't say on it. This is the size of that moon compared to the British Isles, and it's a little bit smaller than the state of Arizona. I should have written it down, but a couple hundred miles across, plus or minus a little bit. I don't have a good feeling for the size of the British Isles. I've never been there. But there are, near the South Pole, there are these funny things they call the tiger stripes. And out of these tiger stripes are spewing fountains of water ice. That it's liquid below the surface and comes spewing out as ice. And whether or not there is, this is a false color just to show how far away these plumes get from the surface of the moon. And they actually, it was already known that there was a sort of icy ring outside of the outer rings of Saturn, and it's right at the place where this moon is. And these plumes are producing enough ice to fill that ring and keep it supplied with these particles. I just went 2 weeks ago to the American Astronomical Society meeting in Austin, and I did go to a talk where people were trying to make observations of those plumes to determine whether or not there was sodium in the plumes. And they tried to find it. Now, the deal was, if it really came from an ocean beneath the surface, that oceans should have mixed in with it not just pure water, but other contaminants. Well, not contaminants isn't the right word, but other elements would be mixed in with the water. But if these plumes came just from ice alone, that was crystalline ice that somehow got disrupted and put into these plumes, then you wouldn't expect to see the sodium. Now, why they were looking for sodium wasn't just because sodium would be the only impurity or whatever in the water, just because the sodium's easy to find in astronomical observations, just because of the nature of the sodium atom. And they did not find the sodium, so it makes them think that the plumes are not coming from liquid water, but that's just one observation. It was recent of interest. So finally, out of our solar system and on to the way that we search for other planets. And I've already told you about how we find some planets based on their pulling their star around. And some of those planets, if it's a sun-like star and a Jupiter-sized planet, Jupiter is 1/10 the diameter of the sun. So if a Jupiter-sized planet passes between us and the sun-like star, it will block off about 1% of the star's light. And even our 24-inch telescope on the Wellesley College campus can measure a transit like that. And after one was discovered to exist, some of our summer students one year went out and made that measurement. And another student did it for another planet this year as a class project. But it works for a Jupiter-sized planet crossing the star, but an Earth-like planet would be the size of that sunspot. And it would only make the star dim by about 1/100th of a percent, a factor of 1 in 10,000. That's a lot harder to do beneath this blurry, smeary atmosphere. And there is a NASA mission called Kepler that is scheduled at this point for launch, and I think it's 2011. It might be 2009. I'm sorry, I should write these things down. But what it's going to do is go into orbit and stare for 4 years at one field in the sky, kind of up near the Northern Cross, and just very, very carefully monitor the brightness of a bunch of stars and look for little dips in the brightness of 1 part in 10,000 that repeat once a year or so. And if this dip happened, repeated several times on a regular basis, and it was that amount of decrease, then you'd be able to tell not only the size of the planet by the amount of light that it blocked, but its year by how long it took to orbit the planet, and then you'd be able to tell if it was an Earth-like distance away from the star. So that's something that hopefully I'll be able to, before I retire in something like 2015, actually be able to say that we have detected Earth-sized planets around other stars. Now, whether or not those are Earth-like and have liquid water on them is a harder thing to do, because you would have to be able to take a spectrum of the planet apart from the star itself. It's very hard to separate those out. Now, some of these giant Jupiters, we are getting information on those planets' atmospheres by taking very detailed measurements with the Hubble Space Telescope when the planet's in front of the star and when the planet's not. and any additional absorption can be from the atmosphere of the planet. And we're getting some neat stuff that way. But if you take spectra of our inner planets from space, you could see that Venus, big absorption due to CO2. Earth has some CO2. Mars, all of us have CO2 in our atmospheres, but there's Earth with its oxygen. It's actually ozone, O3. And there's water you could pick up. This is out in infrared wavelengths. So you could tell, if you could separate out an Earth-sized planet from its star and take its spectrum separately, you'd be able to tell if there was oxygen in its atmosphere and water. Now, something I didn't realize till I'd been teaching astronomy for quite a while is that we didn't get free oxygen in our atmosphere until 2 billion years into the Earth's history. And it was put there by life. It's the waste product of photosynthesis. And for the first 2 billion years of Earth history, the rocks were able to take up the excess oxygen, and the chemical composition of the older rocks on the planet is different from rocks 2 billion years and younger because of the oxygen content. We can tell these older rocks didn't have the oxygen in them, but the rocks can no longer take it out. So, I mean, our planet has already once been polluted by forms of life and changed, and those forms of life had to figure out, they couldn't live in the presence of free oxygen, and they had to figure out evolve or die kind of thing. And now another bunch of us is really changing the whole scheme of our planet. But if we found oxygen in the atmosphere, and particularly in combination with methane, which largely produced on our planet by digestive systems of cattle, although some of it does come from oil areas and naturally coming up from lakes. But any methane that would come up naturally would combine with oxygen and be gone right away. But if you have those two together, either or both of them have to be continuously replenished. So that would be the real tip-off. And there's been a lot of talk of trying to launch a mission that, at one point it was supposed to be 2014, and now it's on indefinite hold, but called the Terrestrial Planet Finder, which would either use several widely spaced telescopes in space. Another option is to block, and then that would be able to separate the star from the planet, or to use a coronagraph, which means block the bright starlight, and then try to find the image and take a spectrum of the Earth-like planet and see if you can find that methane. And that would tell us that there was life. It wouldn't tell us there was intelligent life, but it would tell us that there would be life if you saw those gases in combination. So that's a real brief run-through of how we are going to try to find Earth-sized and Earth-like planets. In the next, within the next decade, we may have found Earth-sized planets, but Earth-like as far as water or oxygen is a ways off yet. But as for searching, another way, again, here is to search for signals from extraterrestrial civilizations. And this is the telescope Arecibo, where this is a whole valley in Puerto Rico, where it had the sort of dish shape that you need for a radio telescope, and then they strung this radio reflective mesh over it. It's like the size of 3 football fields. I think this is the swimming pool for the staff, to give you a feel for the size of this thing. And when they resurfaced it in 1974, this was the only time we've ever really beamed any kind of message aimed out at extraterrestrial life. It was a total publicity stunt. They aimed it at one of the globular clusters that Harlow Shapley used to find our place in the galaxy. They did that for a couple of reasons, one of which is you've got 600,000 million stars all in a compact globular shape, and the beam from the telescope would spread out on the way to just sort of encompass the size of that cluster. So you get several 100,000 stars for the price of one. However, then before the however, and there were some congressmen that were really, really freaked out. You know, you're giving our location away. They're going to come eat us. You know. Number one, globular clusters are made out of these first-generation stars with low abundances of heavy elements. These are not the places we expect to find rocky planets. Number 2, it's 25,000 light years away. 25,000 years, oh, there's food. It's 25,000 light years away. Okay. The other reason that this was nothing more than a publicity stunt is that we scientists want reproducible results if we want to believe anything. We want to hear it again. Their total signal went out for something like 5 minutes. So you can just picture 25,000 years from now, if there were rocky surfaces there, these guys got their radio telescope. What an amazing signal! Let's listen for it some more, and be gone. We've had some things that have been called the wow signal. Of course, some of them have been car ignitions near the radio telescopes. The military had to fess up to some satellites that they hadn't told the scientists about before. But how would we tell that a signal is really artificial and not... I mean, we didn't build that thing just to look for extraterrestrial life. We built it to all sorts of reasons. One of them is to measure... They send radar out from it. They send a radio wave out from it, bounce it off an asteroid. The signal comes back. They can get shapes of asteroids, rotation curves of asteroids. They can map out parts of Venus, which now they can do better from orbit. They study quasars and galaxies and all sorts of stuff. But any natural source of radio emission, it sounds kind of like static over your whole radio dial. A radio station doesn't broadcast over the whole radio frequency range. It picks a narrow band and tells you, listen to 92.1 FM. And now, we would think that an intelligent civilization wouldn't be trying to broadcast across the whole radio band. They'd narrow it down, partly to save energy and partly to distinguish it from natural radio sources. But you don't have the interstellar radio guide. What channel do you turn to? And so there was quite a bit of thought about what would be a logical frequency when the first searches were being done. But now we have developed electronics that can search for narrowband signals over a huge range. So that's what's... they have one piggybacked on wherever this thing is aimed. They can't aim the dish, but they can move the receivers around a little bit so they can study different angles in the sky, different positions in the sky. Any place this telescope is pointed to, there's a receiver on there piggybacking, listening for narrowband signals. Now, those congressmen that were freaked out about us beaming the signal out, whether they like it or not, for 50 years or more than 50 years now, I got to add, I'm older than that, and there's been radio stations and TV before me. Let's say over 60 years, 70 years now, there have been radio signals of narrow bandwidth leaving the surface of this planet and ever expanding outward. Now, the difference between the beamed signal and those is the strength of them. One that this big telescope sends is way stronger than something that the radio transmitter down the street sends. But nonetheless, it's going out there. And the stuff that actually escapes our atmosphere, it's military warning radars and the video part of TV. It's going to put a real good picture of our civilization out there, right? But it would still be detectable as a narrowband signal, but much fainter. For what it's worth, this is the signal that was broadcast when they resurfaced Arecibo. It was a series of ones and zeros that repeated a few times. And the total length of it was the product of two prime numbers. And so if you say, oh, that's 73 times, I'll pick up some other prime number, 37 or something like that. And if you, rather than rearrange it in this long string, and you put it in a two-dimensional grid with one side one prime number and the other prime number, you get this. If you make the ones dark and the zeros white or something like that, there's the radio telescope. These are numbers, the way they code the numbers, and this is DNA, and this is a human, and this is the sun, and we're the third rock from the sun, and they still counted Pluto back then. And but that was to, whether anybody would figure out what it meant, if they detected it, they would be able to tell it was artificial. In order to get something like that for a few tens of light years away, we'd need a collecting area of radio dishes that was a couple of miles across. So it's unlikely to happen soon for us to have that sensitivity. But the Microsoft millionaire or billionaire Paul Allen has been buying off-the-shelf radio satellite dishes and putting together the Allen telescope array. It's somewhere in California, I believe, to actually be used to search for extraterrestrial life. And another big financier of searches for extraterrestrial life, well, it started out in 1492, 500 years later, 1992, NASA says, well, new Columbus thing, we're going to fund the search for extraterrestrial life. Well, no results for 4 months. They said, forget it. And Steven Spielberg took over a lot of that funding because he made a lot of his money off ETs, right? So, but I'm going to end this with how I like to end these talks, with a Pogo quote from the cartoon strip. And a couple of the creatures are out in a rowboat, floating out on a lake or something, talking to each other and thinking, and one of them says, either we're alone, or there really is somebody else out there. Either way, it's a mighty sobering thought. So, I'll be happy to take any questions from anybody.
In terms of the amount of elements, metals you need to make, roughly what fraction of the sun's,
2%.
No. Mm-hmm. No, that's not the question.
Okay, sorry.
How much metal do you need, or heavy elements do you need in the nebula? We had 2%.
We had 2%.
What fraction do you need to get a decent-sized planet,
Well,
in your disk?
The older generation stars that I'm talking about that are mostly hydrogen and helium tend to have 1/100th on average the heavy element abundance that the sun does.
Yeah, that's probably too little.
And that is probably too little, but there are some people who argue it's enough. And I don't have the numbers on the top of my head, but I think it's just like 25% more than our sun has. So it's not even 3%. Is where you're starting to see these disks where the heavy elements are enough to start the migration inward. So I'm sorry I can't give you better ranges than that, but that's what I know about. Whatever I say is, I would think is.
I'm looking for the lower bound.
Yeah, and that's
The first generation of stars couldn't do it, but how far back in the history of the galaxy could you go?
That also depends on the location. And I'm not able to give you an answer of if there's half the metallicity, would it work? But I am going to say that the star formation happened earlier in the center parts of our galaxy, and the zone of the right metallicity is gradually moving outwards. So it could be that there would be older civilizations closer to the center of our galaxy, and it's just our turn now, and then it will be moving outwards. So there could be a very long time period over a galaxy that could have happened, because the very earliest stars nobody's seen them unless we see them way out. I mean, even our current oldest stars in our galaxy don't have 0 heavy elements, and it's been kind of, I don't know all the details. It's been kind of fun reading up on what they think the earliest stars might have been like, and they could have been much larger and therefore last much less time.
Talked about Kepler, talked about silicon base. How much does this?
I don't know. What I have heard, I'm not a chemist at all, and I just read what are in standard things that astronomers tend to look at. The one thing I have heard though is that the carbon with its double bonds are just the right strength to be able to be broken up in the right ways, whereas silicons aren't. And your hand, can you answer that?
I have read enough about the chemistry of both elements to read some people trying to study what you could do with silicon. It turns out to be bond strength, according to this particular author's point of view, a bond strength issue. The bond strength of carbon with carbon is comparable with its bond strength with other elements like oxygen, nitrogen, hydrogen. So that makes it easy to form carbon chains very, very long. Silicon bond strength with itself tends to be a little bit weaker than its bond strength with oxygen, hydrogen, nitrogen, whatever. So it's hard to, they've gotten silicon chains up to about 8. But much longer than that, something else comes along and says, silicon says, I'd rather be
With you,
bound to you than to my other silicon. So
I'd rather be bound to oxygen and make a nice rock. Yeah.
In that case, it looks like to me, carbon-based life is more, possible and more probable in general.
And that is the current best viewpoint among the astronomers, but there are people working on others.
Question. You talked about possibility of life closer to the center of the galaxy. Wouldn't there be other issues with that because of, for galaxies that have active galactic nuclei or really...
Yeah, there could be, but...
Stars or...
Yeah, there is a big black hole at the center of our galaxy, and right now it's quite quiescent because nothing's fallen into it. But, again, I won't say again, but we are 10 kiloparsecs. We're about 30,000 light years away from the galaxy's center, and even 10,000 light years away, you're not going to have, from the size of black hole that we have, probably isn't in the inner, few hundred parsecs or something could be pretty evil, but, halfway out, where the star formation would have happened more earlier, is not going to be trouble from the black hole in our galaxy, I don't think.
Have they come out with...
Oh, they may have, but it's... have you seen one, or... Pardon?
I'm asking you, since you are so familiar...
Yeah, I haven't seen anything more expanded than that. It really was just a guide to get them thinking about making those estimates. But it is taught in a lot of textbooks right now, just as a guide and as a historical interest. Because of, the big uncertainties in the L for life and stuff, is the lifetime, it's tough. Well, the binary stars you take care of in the R sub star. That's where you say rate of sun-like stars. And so that R star number at the beginning includes leaving out the binaries. So that they get put in that term. I probably neglected to mention that at the beginning here, but that's where the binaries are taken care of. That is, yeah. You had to come in a couple minutes late, didn't you? Because I went through that stuff like right at the beginning, and the carbon-based stuff, so yeah, it's the just to recap really, really quickly at what I said in the beginning. Not only does carbon make all the complex bonds, but liquid water with its polar molecules can move these things around, and it's liquid over a large range of temperatures, which is right at the right temperature for the carbon chemistry to happen. So other astrobiologists are working on other things, but carbon and oxygen are very abundant and therefore likely to be around, and therefore most effort is going into looking for Earth-like life.
We're looking for carbon-based life in the
Right, like water. And that is the tack by looking for Earth-like planets with the oxygen in their atmosphere. The radio signal method does not depend on the life having any kind of particular biological structure, just that it know how to use radio waves.
But we may be able to find life not like intelligent, because this is something which might be some kind of life.
Yeah. And would we recognize it if we saw it? Is another question to that. Okay. What my research is on is it's a double star system where the primary is a great big, late in its lifetime. If I say M supergiant, it's a cool supergiant star that's losing matter. And it is being they're orbiting around each other. Another massive but main sequence, which is the long phase lifetime like our sun is in now. But it's smaller, and as it goes out of eclipse, the light shines through different layers of the atmosphere. And I've got spectrum from the Hubble spectra from both the IUE satellite and the Hubble Space Telescope in the ultraviolet to study the structure of the cool star atmosphere as the hot star passes behind it. And we thought that the hot star would come completely out of eclipse and you'd just see a typical hot star spectrum, but you don't. You see a spectrum that has a whole bunch of extra absorption in it. And it turns out that that star within the Pleiades has a spectrum with a whole bunch of those extra lines like the one I'm observing. And so it was nice to find that there was another star in the sky that was as complex looking as the one I've been interested in. And so that's why that star is my friend.
She's using Kelly to look for...
Yeah, I got to speak with her. She has to teach tonight. That is one of the ways... Well, that is one of the ways in which if you found... What chirality is that the amino acids in our bodies, the basic building blocks of proteins, can form, they have identical structures, but they can be mirror images of each other. So you can have a left-handed versus a right-handed, the way the molecular structure is. And all of Earth life is based on the left-handed structure. And any kind of natural experiment that you do, there was an early experiment done about the same time as the Drake equation was devised, in which they made these amino acids in the laboratory by putting together a particular chemical composition atmosphere and just zapping it with electric sparks to provide energy, and this organic goo was made, and it contained a whole bunch of these amino acids, but it was an almost equal mixture of left and right. And there are meteorites that have landed that have amino acids in them, and it's a pretty much equal balance of left and right. And so one of the ways in which we would, if we were to find complex molecules from some extraterrestrial source in which we would believe that it was life instead of not life, was to have a predominance of one of these handednesses. And if there were amino acids in it like ours, but they were all left-handed like ours, then you couldn't say that it was a separate occurrence of life. But if they were all right-handed, then it would be completely different from Earth origin. And so apparently from what I understand that she's working on is how did this one-handedness come to be in the first place in Earth life? Was there more of one than the other, and then Earth life fastened on that and only used it? So that's about all I know about chirality. Do you know anything more that you could share?
No, I was just wondering...
I spent a whole semester on this subject. I can't do it all in 1 hour, but that is one of the ways that we would use to try to see if life was extraterrestrial or not. Okay.
If there's no other questions, I'd like to thank our... Thank you for coming out, and there is a sheet on the way out, and if you're interested in information about the physics program or any of our talks, please sign it and leave your email address. And this is the first in a series of lectures. The other lectures this semester are going to be on Monday evenings at 7 p.m. in Bayou 33, 23rd floor of the Bayou building. And all this information you can find, 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 and all this information you can find.